Oh, see, it's very because I'm using the PDF. I'm not sure. Like sometimes the PDF cannot be at the display on the projector. Yes. But what I said is like so everything on the screen just displayed on the projector. So it's good. Is there a microphone here? Oh, you put it. Oh, okay. So maybe turn it on after 2 minutes. Yeah, just. Okay, I'll sit in the. Okay. Hi. I think we can maybe start now. Yeah. Yeah. So, hi everyone. So thanks for showing up. First, I maybe introduce myself. I'm Kevin. I'm currently working in the department as a research fellow. So in this week and the week after next week, I will help Gayatri to give 2 lectures on the topic of error correction coding in wireless communication. So this is my email address. So please feel free to send me one email if you have any questions. I will be more than happy to answer any questions. So this is my name. You can call me Kevin or Cui Wei, whichever you feel like to. Yeah. Do you have any questions before today's lecture? Otherwise, we will start. Yesterday in Gayatri's lecture, I did a small survey. So to check your understanding on the topic of error correction coding. So this is the result. I checked the 6 topics, which I'm going to cover in this lecture. So the green part shows the number of students who have never studied error correct coding before. And the blue part is the students who have studied but with limited understanding. And the yellow part shows the students who are really good at this topic. So then I realized more than half of students for each of the topics have never studied this before. So in today's lecture, so that's why I'm going to make the speed slow and to make sure that everyone understanding what is happening. Yeah. So hopefully after today's lecture, you can at least say that you are good at some of the topics in error correction coding. So in today's lecture, I will cover the basic method or algorithms used in error correction coding. So first is the background, in which I will explain what is error correction coding and why we are using error correction coding in wireless communications. The first topic will be the parity bit. So parity bit is one of the simplest way of doing error detection. So I will give examples to show how it works. So actually, we have to pay attention that error detection is different from error correction because many of the algorithms can only be used for error detection, but they cannot correct errors. So just pay attention to this. So the second topic is the linear block code, so in which I will also use like multiple examples. So we will do it together to see how the encoding process works and how we can still successfully decode the transmitted message even with transmission errors. So my plan is today's lecture, we will end up here. And we see that, but the plan is for the week, the next week is holiday, so the week after next week, we'll start with convolutional code. So also, for the encoder part, I will use a specific encoder structure to give you the idea how the convolutional code works. And also, we will go through step by step how to show how the Viterbi algorithm can be used to efficiently decode the transmitted message. I'm sure after this part, you have better understanding of the Viterbi algorithm. So the last topic I'm going to cover is the tuple code. So the tuple code actually is a very popular coding method. It's used in the current LET standard. So the idea of tuple code is pretty straightforward. It's used two convolutional encoder, and in the decoder it's used two convolutional decoder, and there's the software information exchange process. So however, actually, it's very difficult to explain all the details within only 2 lectures. But I will still cover the concept of tuple code. But if you have any question you want to know, I would be more than happy to explain after my lecture. So, so here's the background. So why we are using error correction code? So basically, it's because we always want to make sure that the received message is correct. It's always the transmitted one. That's why we are using the error correction code. So for example, here's a typical transmission link. So in which we have a transmitted message M, which has k bits. So this M is then sent into an encoder to generate a code word C, and C has n bits. So normally n is larger than C, so we make sure that redundancy is introduced. So next, after we have the code word, so we modulated the code word onto an RF signal. So I think Guthrie is covering the related topic for this part, like how the signal processing works and how the modulation process works. So I will not talk about the details here. So after we have the code words, it will pass through a channel, which usually have fading, attenuation, and in the receiver we have noise. So the received code words will not be the transmitted one. So it normally have errors. So for instance, here we have a single bit of error. So the received code word is then sent into a decoder. And then we can, from the decoder, the output, we estimate the transmitted message. So here's the quick summary. So we have a message sequence. From the message sequence, we send it into an encoder. We generate a code word. And the code words pass through the channel. We have the received code word, which normally have error. And from the received code word, we estimate the transmitted message. So the concept, the benefits of using error correction coding is even there are transmission errors, we make sure that either we can detect the error, or we make sure that the estimated message equals the transmitted one. So this is hat M equals M. So these are the why we are using error correction coding in telecommunications. So we go to the first topic, so parity bit. So parity bit, as I explained before, is one of the simplest way of doing error detection. So it's only for error detection. So here's the definition of parity bit. So a parity bit is basically just a single bit, which is added into the binary sequence to make sure the overall number of ones in the sequence is even for even parity and odd for odd parity. So we have to pay attention. There are 2 different types of parity bit. The even parity is make sure that overall number of ones in the sequence is even, and odd parity is make sure the overall number of ones is odd. So basically they are the same thing. So in my example of today's lecture, I'll just focus on the even parity bit. So here's one example. So basically after we got the transmitted message, we check how many ones inside the sequence. You can see that there are like 3 ones, which is odd number. So in this case, we generate a parity bit of 1. We put it in the end of the sequence. So in this case, the overall number of ones in the sequence is 4, which is the even number. So this is how it works. And another example, so if we have like 2 ones in the sequence, which is already an even number, So in this case, we generate a parity bit of 0, and we put it in end of sequence. So that, because it's already the original number of ones is already even, so we just generate a 0. So there are two different cases. So also for the receiver side, also have different cases. The first case is when there's no transmission error. So we can see that the received one is exactly the transmitted one. So in this case, the receiver check how many ones in the sequence. It's 4 ones, so it's an even number. So in this case, the receiver will make a decision, there's no transmission error. So everything is correct. So which is also this case. It's correct. So the second case is when the number of error in the transmission is odd. For instance, in my example, if there's a single bit of error happens here. So we still check how many ones in the sequence. We can see that it's 3, which is odd number. So in this case, the receiver will know, something wrong. So in this case, the receiver will send a request back to the transmitter, and transmitter will send the message again. So until the transmission became successful. So which also do the work is there's some error, it can detect error. So for the third case, so when the number of errors is even, so for instance here, we have 2 bits of error. So if we check how many ones in the sequence, we can see that the number of ones are 4, which is an even number. So this will cause a problem because the receiver will assume that there's no transmission error. So however, which is not the case, we can clearly see that there are 2 bits of error here. So in this case, it will not work. So I have a quick summary of the parity bit because it's very simple. We will not spend much time on this. So the first is its advantage. So it's very easy to implement because the logic is very simple. But it has disadvantages. For instance, it can only detect error, but unable to correct errors. So if something wrong, the transmitter have to send a message again, which is not very efficient. Another disadvantage is that it can only detect odd number of errors. For instance, in the previous example, we see that if the number of errors is 2, it will not work. So definitely we can do much better than the parity bit. So I actually did a small research on the parity bit to see whether the current wireless communication standards are using the parity bit. It seems not, but in some of the networking error detection, I think they're using the parity bit. So the next topic is linear block code. It can achieve much better performance than parity bit. It not only can do the error detection, but also can do the error correction. So basically, the linear block code is if we have overall transmitted sequence, we divide it into multiple blocks. For instance, each block we have let's say kbs. So we send each block into what we call linear encoder. So we generate a code word which has n bits. So normally n is larger than k. So we make sure that redundancy is introduced. We have more flexibilities to do the error correction. So I will explain why it's called a linear encoder, because it's nothing but like a linear operation. And will be much clearer after one example. So I give one example of 3-7 linear block code, which means the message sequence has 3 bits, and code word we generated have 7 bits. So this is the M is the message sequence, 3 bits, and code word is the C, which has 7 bits. And this is how we are going to generate the code word from the message. And we have to pay attention that all the plus symbol in my slides are the modular 2.8. So this is the table, what is the modular 2.8. Because many of the literatures, they use this symbol for the modular 2.8. So it's nothing but an XOR gate logic. So we just pay attention to this. All the plus symbol in the slide is modular 2.8. Maybe. So this is how we are going to generate the code words from the message. So for instance, the first bit in the code words is is the sum of all the bits in the sequence, which is M0 plus M1 plus M2. And the second code word is M2 plus M1 plus M2. And this is how we calculate third, and fourth. And more interesting, we see the last 3 bits, C4, C5, C6, is nothing but the exactly copy of the message sequence. So if we write them into a sequence, it looks like this. So if you see the last 3 bits, it's just exactly copy of the message sequence, and the first 4, we call this data bits, and the first 4 bits is the parity bits, and each bit is a combination of all the message sequence. So here's the table of all the possible combinations of the message sequence and its corresponding code words. So because we have 3 bits of the message sequence, so 2 to the power 3, we have 8 combinations, which is all listed here, from 000 to 111. So, and these are the corresponding code words. So if we check the last 3 bits inside the code words, it's nothing but exactly copy of the message sequence. You can see that 111 is copied here, 00 is copied here, maybe 100 is copied here. So, and the first 4 bits are the parity bits. How we got the first 4 bits is using this calculation. We can use one to check whether how we are doing this. For instance, the first bit in the code word is just M0 plus M1 plus M2, which is 1 plus 0 plus 0, which is 1. And the second bit in the code word is M1 plus M2, which is 0 plus 0, which is 0. And third one is M0 plus M2, so it's 1 plus 2, which is 1. And also the other one is also 1. So basically, if we input a message sequence into the encoder, 100, and this is what we get from the encoder, which is the generated code words. So after today's lecture, if you have free time, you can check all the others, how you, from the message sequence, and you input into the encoder, and how you can generate the code word. So the encoding process can be expressed using a linear matrix calculation. So we can use a matrix to describe the encoder. I will use one example to explain why it is a matrix. We'll be much clearer about that. So basically, what we input into the encoder is a sequence vector. M has n bits, and generate the code word which has this M have k bits, C have n bits. So this is the coding process. So it's nothing but a linear operation. That's why it's also called linear block code. And the G is called the encoder matrix or generator matrix. I think this is the most popular name. So it's a generator matrix which can be used to describe the encoding process. And we will use this example to check why it's a matrix. So in the previous example, this is how we generate the code word for the different bits in the code words. So we can see that the first bit in the code words is M0 plus M1 plus M2. So it's just a matrix calculation. So that's why there are 3 ones inside vector. And the second bit in the code words is M1 plus M2. Because M0 doesn't contribute to the second bit, we can see that this element here is 0, and the other 2 elements are 1s. So same, you can check this one is corresponding to different columns in this matrix. And because the last, just get back. Because actually the last 3 bits in the code words is just exactly copy of the message sequence. So that's why this part is a diagonal matrix. So basically, the encoding or the encoder can be described using a matrix. So that's why we can just use a matrix to describe the structure of the encoding process. So in this slide, it's just a general description of the encoding process. We have a generator matrix, has a size of k by n, and we have an input sequence. The message was 1 by k vector, and this is nothing but exactly another way to describe the generator matrix, which has a size k by n. So in this case, we generate a code word has a size of 1 by n. So this is just the encoding process. So the encoder is systematic if it has a format of this. So in which I key is a key by key identity matrix or diagonal matrix. So it has something. Just make it clear. So it's a key by key diagonal matrix, and the Pn is a key by n minus key matrix. Also, the generator matrix of a non-systematic encoder usually can be simplified into a systematic format. So what I mean systematic format, because do you remember in the previous example, we copied the message sequence exactly into the code word. So that's why we have a diagonal matrix inside the generator matrix, but which is not always the case. In some of the encoding, it depends on how you design the encoder structure. In some of the method, it's not copied exactly into the code word. Each bit inside the code word is a combination of all the bits from the message sequence. But as I explained here, so even if it's a non-systematic encoder, it can usually be simplified into a systematic format. So in today's lecture, we just use the focus on the study of the encoder which has a systematic format. So because G is actually can be written as P and IK, so which is M, P, and M and IK. So this is just exactly M. So this is the copy of the message sequence, and this is the parity bits. So we can clearly see that redundancy is introduced. So in this slide, I'm going to show what is called the parity matrix. So parity matrix actually is very important, used in the error detection, and it also shows the relationship between different bits inside the code word. So in the previous example, so this is how we did the encoding process, and from this part, actually we can get a relationship to here. So this is because you see C0 actually equals M0 plus M1 plus M2. M1, which is C4, M2 is C5, M1 is C5, M2 is C6. So basically, C0 equals to C4 plus C5 plus C6, because we are using the modular 28 here. So it's 0 plus 0 equals 0, 1 plus 1 equals 1. So basically, because C0 equals to C5 plus C5, C4 plus C5 plus C6, that's why when they add them together, it's 0. So for instance, for the second, how we get this one is because C1 equals to M1 plus M2. M1 is C5, M2 is C6. So C1 plus C5 plus C6 equals 0. So everyone clear about this part? Yeah, I think it's pretty straightforward. So basically, this is the relationship between different bits inside the code word. And we can also further write it into a matrix format. So it's very straightforward. So because for instance, the first relationship is this, because like a C1, C2, C3, it doesn't contribute to the first equation. So that's why there are 3 0 elements here. So it's the very basic matrix calculation. So we can get the value from the first row, and for the second row, which is C1 plus C5 plus C6 equals 0. So we can see that the corresponding elements are 1s. That's how we get the second row. So basically, it's just another way to show the relationship between different code words. So this matrix is what we call parity matrix. So it's just this matrix. So one important property of the parity matrix we can see, so it's nothing but this equation. So the parity matrix multiplied by the code word. So I use a transpose symbol here because it's in the vertical format. So it's a 0 vector. So this is very important property, and we use this property to do the error detection. So I mean, if there some error happens, so what you receive is not the transmitted code words. So if you use the received one multiplied by the parity matrix, so it will be no longer 0. So we are using this property to do the error detection. So I will explain this soon using another example. So one question is like, can you see the relationship between the generator matrix and the parity matrix? Is clear or not? Maybe it's not clear, but if I put them in the same place, maybe can you see the relationship between the generator matrix and the parity matrix? So we can see the generator matrix is, we can see this part is the diagonal part, which corresponding to the exact copy of the message sequence, and this is the corresponding to the parity bits. And if we check the parity matrix, so it also have a diagonal matrix here, but the interesting is if you check here, which is nothing but the transpose of this part. So you see, so it's nothing but the transpose of the generator matrix. So basically, if we know how the encoder works, how it, what's the generator matrix looks like, so we can have we know how what's the parity matrix looks like. So in the receiver, because the receiver has to know how the encoder works, otherwise it cannot decode the code word. So if we know how the encoder works, it will know what the generator matrix looks like. It will know the parity matrix looks like. So this is the information the receiver will have. So again, this is the property. We are going to do the error, the decoding process, and also the error detection process. I will use example. First, I have a quick summary of how the overall process works. We first have a message sequence, which is input into an encoder, can be described using a generator matrix G. So then we get a code word. It's nothing but like a linear calculation, and the code word will pass through the channel, which it can be written in this format. It's code words. This is called an error vector. So it's like, for instance, if the error vector is 0, 1, 0, 0, this means the second bit in the code word is like it's flipped. So it's indicate the position, location of the error. So this is so in the receiver. So we have the received sequence. So based on the parity matrix, because this is the information we assume the receiver know, and based on this information we can estimate the error vector. I put a question mark here, how we are going to estimate the error vector. I will explain later using one example. So after we estimate the error vector, we can estimate the code words using this basic calculation. And from the estimated code word, we can further estimate the message sequence, because each like a message sequence, it has a unique code word. So the relationship is unique. So this two steps will be very straightforward. The question is how we are going to use the parity matrix and receive the sequence to estimate the error vector. So I'm going to use the example to explain. So here also another important definition is called syndrome. So syndrome is just basic. It's nothing but the parity matrix. Yeah.
This is R minus E hat or plus E?
It's plus, because if you check, it's modular 2.8. Yeah. If you, I think later we can use one example. You see that example because it's modular 2.8. Even here it's plus, but it's still plus. Okay. Yeah. So it's make sure that all the plus here is the modular 2.8. I mean, you mean this one? Yeah, this one is still plus. Yeah. So you can check that. So it's not like I understand what your question. You say that R equals C plus E, C equals to R minus, but it's modular 2.8. It's not the plus, the normal plus. You can double check that when yeah. So now we get back to the syndrome. So the syndrome is nothing but H multiplied by the received sequence, which is the received sequence equals to C plus E. So we can easily get here, then further get to this step. And because this part is always 0, as we explained this is the property of the parity matrix. If you have a code word multiplied with the parity matrix, it's always 0. So you can get syndrome is nothing but h multiplied by the arrow vector. So the process is, in the receiver, we have this part, and we know the h. We can calculate the syndrome, and we know the syndrome equals to h multiplied with the arrow vector. So now we have this relationship. So we know what is S, because this is what we can calculate it. And we know what is H, the parity matrix. Can we estimate from this equation? So it's a vector matrix relationship. I will use one example to. So here's just a quick summary of the size of the syndrome, size of the parity matrix, and size of the arrow vector. So it's not very important. So in the receiver, we'll do the first step we are going to do is we calculate the syndrome. If the syndrome is a zero vector, we say, oh, there's no transmission error. Everything is correct, because this is the property of the code word. So, but which is not always the truth. Because sometimes if the arrow vector equals to another code word, even the syndrome is zero, there's still errors. So it depends on how we are going to design the structure of the encoder, and depends on the like how many errors it can be correct. So it depends on the minimum Hamming distance of the code words. So I will explain why the minimum Hamming distance later in another slide. So the first step, we check whether syndrome is zero or not. So the syndrome is HR. I'm not. So we first check whether this is zero. If this is zero, everything is done. There's no error. Whether it's correct or not, we assume there's no error. But when the syndrome is not zero, so what we are trying to do, we are trying to estimate the arrow vector. So then we can further estimate the code word. So the question is how we are going to solve this equation to get the estimated arrow vector, because it's a equation, the matrix vector calculation. So if we write this, we can actually have an equation set. So for instance, we have the arrow vector, which is E0, E1, and E2. If we have 3, and if the let's say if the parity matrix, for instance, is 0, is this, and we'll get maybe 0, 1. I'll just give one example, because it's basically this equation. If we write this into, we can get E1, E0 plus equals 0 from this calculation. And from the second row in the parity matrix, we can get is E0 plus E1 equals to 1. So we can see that we have 3 unknowns, which is E0, E1, and E2, but we only have 2 equations. So the solution is not unique. So for in this case, the solution will be E0 equals to, the writing is not very good. So the first solution is E0 equals to 0, and we get E1, it's 1, and E2 can be anything, can be 0 or 1. So we have 2 solutions. So which one is the good solution? The good solution is the one with minimum Hamming weight. So I will explain later why the minimum Hamming weight one is the optimum solution, which can is equivalent to the maximum likelihood decoder. So I will go through the process again, like to make sure that everyone is clear about the process. So we have a generator matrix, which is the one we used in the previous example. From the generator matrix, we can get the parity matrix, which is nothing but so this part is the Hermitian. So these 2 parts are the diagonal matrix. So the message we are going to transmit is 001, and if we input into the encoder, so what will be the code word generated? Can you just do a quick calculation? Hopefully you cannot see the answer. Yeah. It's a basic, very basic vector matrix calculation. You can see the answer, maybe. So this is the input. So this is the encoder matrix, and what is the output? So it's just mg, so which is the output we want. It should be not a difficult. Yeah. Yeah. So hopefully no one is confusing about this process. So we have an input, which is M. We have an encoder, which is G. What is the output? So is everyone correct? Yeah. So this is the process at the transmitter. So after the code word passes the channel, it will have errors. For instance, if there's one error happens in the second bit, so can we still successfully get the estimated version of the message, which equals to the transmitted message? So this is what we are going to do in the next step. So the first step, we check the syndrome, whether the syndrome is 0 or not. Anyone want to calculate the syndrome, or I will just give the. So this is the parity matrix, and this is what we received. If you guys see the next step, this is what we received, which has a 1 bit of error. So the syndrome is the parity multiplied by the transpose of the received sequence. So we can check that. For instance, if here you can see that I'll not do the calculation anymore, so it's basically 0. So we found that the syndrome is not the 0 vector. So we get the conclusion that, there's transmission errors happens. So the receiver know, what I'm going to do next step is I'm going to estimate this error vector. Then further I can correct this single bit of error. That's what the receiver is going to do in the next step. So now we are going to solve this equation. We know what is S, which S, the syndrome is here, and we know what is parity matrix. The parity matrix is here. So next we are going to solve this equation to get what is the error vector. So as I explained in the previous slides, the solution is not unique. We have, because if we write them into equation set, the number of equations is actually less than the number of unknowns. So we have multiple solutions for this one. So actually I use like a MATLAB code. It's very easy to do. You can get all the possible solutions for this equation set. So these are all the solutions for this problem. So this is all the possible solutions for this problem. So which one is the best one? I already give the answer here. We want the one with minimum Hamming weight. So Hamming weight means basically it's the number of ones in the sequence. We want the one with least number of ones. So the answer is this one. So this is the estimated error vector. So we can see that the estimated code word will be the received sequence plus the estimated error vector. So this is the estimated code word. So because in the previous, we have a table. Maybe I'll go back to here. So I remember, first check. So it's 111, 000, and 1. So if we go back to the original table, so it's 111, 000, and 1. So we found its corresponding message, which is 001. So this is how the decoding process works. So let's get back to the page. So we can see that, because we got the code word, and we can find its corresponding message sequence, which is 001, which is exactly the one we transmit it. So that shows this encoder structure. Even we have one error happens in the transmission, we can still successfully decode the transmitted message. So this is basically the idea how the linear block code works. So is everyone clear about the steps? Yeah.
How do you decode from C hat to M hat?
So that's why
without knowing that we send this message.
Without knowing which message?
Without knowing that we send the M.001 at the beginning, how do we decode it?
That's the. So now it's the decoding process. We don't know that because I assume that because we go through the transmitter process, but the receiver don't know because we didn't use any information of the transmitted message. We just get the estimated M based on the. So this part. So how we get this is we based on the received one.
The last part. 001 in the generator metric you have I, right? So that's why.
Which one?
In the generator metric you have I, you have P and I. So
yeah.
The I one that we send just the message.
Which slides you are talking about? I'm sorry. It become confusing.
Slide 15.
15. Okay, let's get back to the 15.
Yeah.
Yeah.
Because the G still have I.
Yeah.
Yeah. So that's why the last 3 bits has a message.
Yeah.
So we can decode that, right?
I mean, you can do that, but sometimes if error happens in that, for instance, so what the example I gave, the error happens in the parity part, in the first 4 bits, but there will be situation where the last 3 bits, that's why we introduce redundancy in the code word. I mean, if the error happens, for instance, so it's just the example I gave to you, but if, for instance, if this is the code word, if error happens here, for instance, what is 0, so can we still, I mean, based on your method, you just take the last 3 bits, which is not correct. I mean, that's why, so it's not only based on a single part of the code word, it's like a combination of them. Yeah, it's clear? Yeah, it's not like a, that's the, like actually what's the function of the first 4 bits. It carries additional information. So even like something wrong here, you can still get back to the correct message. Yeah, is that correct? Yeah.
After estimating this C hat,
yeah.
Which one of the code words did you calculate the Hamming distance? The Hamming distance that you said that you
I actually here I found the arrow vector with minimum Hamming weight. So, which actually is equivalent to the one with minimum Hamming distance. I think I will maybe in the next slide I'm going to talk about the Hamming distance. You can use them different ways. There are like multiple solutions to solve you can, but I don't think the computer will do that. Yeah. Yeah, it's actually it's not very difficult to do in MATLAB. But for sure, there are like how in terms of hardware implementation, there are definitely some ways of doing. So it's a very common problem. Yeah. So I think maybe what's the next one I got? So I hope everyone clear about the process. So what's the encoding process and how we decode the message even there's errors. Like I try to make, actually I prepared 2 versions of slides because based on the survey yesterday I plan to use this one because this one have more examples. Yeah, hopefully you understand the logic. So the next part is about Hamming distance and Hamming weight. So Hamming distance is the number of positions at which the corresponding bits are different between 2 code words. For instance, if we have a code word 001, another code word maybe is 111, so the Hamming distance is just 2. So if we, the minimum Hamming distance is just the minimum distance in a set of code words. if we have a set of code words which has maybe another one, maybe 0, 0, so what's the minimum Hamming distance? So here's the distance 1, here's 3, so the minimum Hamming distance is 1. So because why I mentioned the minimum Hamming distance is because it's related to the ability of the how many bits of error the decoder can correct. So for instance, this C1 and C2 are like two code words in a set of code words which these two have the minimum Hamming distance. And the distance is like actually 2D plus 1. So actually, like, I mean, if we want to express a code word by a point, which is here, is because it's in high dimension, because C is a vector, so it has n elements, so it will be in the n dimensions. But for like a clearly explanation, I just reduce the dimension into like a one dimension. So C1 and C2 are the two code words in which their distance is the minimum Hamming distance. So for instance, C1 is transmitted, but what we received maybe is not what we transmitted. So maybe what we received is R. So the distance between the Hamming distance between R and the C1 is less than the Hamming distance between R and the C2. So in this case, we will assume that because it's more close to C1, so C1 is transmitted, even what we receive is R. So in this case, we can correct the error. That's how it can do the error correction. So when the minimum Hamming distance between inside of code word is 2D plus 1, so it has the ability to correct the dBs of error. So let's give another example. For instance, if the R is not here, even C1 is transmitted, but what we receive, the R maybe is here. So in this case, the C1 R or the RC1 is larger than the C2R, which means it's more close to C2, so it has less distance. So in this case, we will assume that C2 is transmitted, which is not correct. So I mean, it's the ability of the encoder, how many bits of error it can be correct. It will depend on like how you design the encoder structure and what is the minimum Hamming distance. So hope everyone is clear. So I mean, after today's lecture, you can go back to our example. You check like what's the minimum Hamming distance inside between the code words. So we have like 8 different code words. You can check the minimum Hamming distance. Yeah, just write some MATLAB code that can easily do that. So this is the because last time I saw email people are discussing about why I didn't reply, but I saw the people are discussing why the maximum likelihood decoder is equivalent to the one which can minimize the Hamming distance. I'm not sure whether the people who is asking that question is here. So that's so if we have time, I can let's get back to maybe one problem. Do you want to like solve one problem, or we just keep on doing the next topic will be the convolution code? We can keep on going, or do you want to have a better understanding? Why the better understanding? Yeah. You want to have a better understanding, we can get back to a problem. This one with no solutions. Do you feel I'm explaining too fast, or I'm trying to be like give all the details step by step, make it simple? Let's look at this problem. Okay, let's see whether the pen works. So let's look at this problem. So this basically this problem. I'm trying to answer the question why the one with minimum Hamming distance is equivalent to the maximum likelihood decoder. Why we found the one with minimum Hamming weight, or the code word which has minimum Hamming distance to the received message is the one can give us the optimum performance, or the more likely to be yeah. Okay. So is this better? So this problem. Basically what we are trying to do is like we want to find the, so for instance, we want to find the one with, so the code word which can maximize this probability. So like what's the code word can maximize the probability of C is transmitted by given the received sequence. So this is the thing we are trying to maximize. So which like code word can maximize this probability? That is the question. So actually we found actually based on the Bayes law. So P C so equals actually P PR. So hopefully everyone's clear. So this is the, so because the probability of this is the priori probability, which is PC, which is like for all the code words they have the equal probability. So basically what also this is the same for different code words. So what we are trying to, I'm sorry, it's maximize, it's not minimize. So what we are trying to maximize is this one. So we are trying to maximize and I think this probability is the posterior probability. I think it's very it's easy to do the calculation. So is everyone clear about this part? So the probability is getting, when this one is transmitted, what's the probability the R will be received? So it depends on how many bits they are different. For instance, if the Hamming distance between C and R is D, so what's the probability C is received when R is received when C is transmitted? So the probability becomes so. For instance, so this channel, are you familiar with the bandwidth symmetric channel? So it shows the probability when the error will happen. So it's something like this. So it's 0, 1, 0, 1. So the error, it happened from 1 to 0 is P. From 0 to 1 is also P. So this is the probability that error will happen. And the probability error will not happen because when we transmitted 0, what we receive is also 0. So the probability is 1 minus P. And this one, what we transmitted is 1, and what we receive is also 1. So the probability is also 1 minus P. So the problem now is we are trying to get this probability, and this probability is nothing but equals to
P to the D.
Yeah.
And 1 minus P.
Yeah, P to the D and 1 minus P.
P.
N minus D. Yeah, exactly. So then this one we can, I'm sorry, it's slightly messy because I'm writing on there's no